Welcome everybody to another Earth2Class program. And today we are pleased to welcome for the first time Chia Ying. She is at Lamont and she's going to tell us something about her research into hurricanes. So Chi, whenever you'd like to take over, you can. You can share the screen.
Let me share the screen. I should
Yep,
go
it's
out.
on.
Yes.
May
All
want
right.
to go back to the beginning.
Yes. So you guys see the right screen, right? Not the presenter's mode, just to make sure.
Yep, that looks like before a hurricane.
Good. So today I want to talk about weather system in the tropic. I believe Christiana is familiar with the view here. You have Kansi, white sand, palm tree, sunny. Until when the system I want to talk about happen, which is a hurricane, and the nice beach will become like this way.
Oof.
So the hurricane is actually the concept or the idea of hurricane or even the word of hurricane comes from Spanish explorer that of the New World who were told of an evil god of the wind that causing huge destruction. So it may come even earlier before the explorer. The symbol on your left is a god of hurricane from Cuban ceramic, like engraved on the ceramic mass and vase. And according to the literatures, that the native Caribbeans are very feared of the god of the wind. So when the wind comes, they will play drums and do some like a bizarre ceremony, try to attempt to drive the god away. Now, all the way to the east side. The figures on the right is from one of Dunhuang mural painting, and that also just show you there's a wind of God, and how the God blow the wind is by play those like wind-induced instrument. So if you see again, go back to the God of Hurricane symbol, you can see some similarity between the old symbol to the new current symbol we use for tropical cyclones. You just need to turn your head around a little bit and you see the similarity. Now, so we can also look at the description of hurricane from the old literatures. And this is from, I think it's from sailing vessels. They happen to happen in the hurricanes in the 1869. And what it says is there's a scalding wind and ambitious ocean swell and the rage and the foam, which kind of describing the sea state of the hurricane and also the strong wind inside the storms. Similar article, well, not really similar, but we can also find an article in the old Chinese article. No one will understand here, but there's a translation. It's basically found in Guangzhou area. They're talking about how there's an event with wind from all direction, and it can usually happen in June and July, and last as long as 7 days, as short as 2 days. So those kind of description and the pattern and the things they kind of engrave in the vase give us a basic idea of how hurricane may look like. We know it can be coming from all direction, and we know it can stay here a day to 7 days, and we know it gives you a rough sea. But now we have better idea of hurricanes. So here is a view of hurricane, which we can already see from the space. So I think this is one is Florence, and you can see a clear spiral shape of hurricane, like donut, but they have a spiral shape. And then there's a centered around, so there's a center kind of have like a no cloud. So, or if we zoom in, we can see those like a no cloud center, because we call it as I. And the strongest cloud, the thickness, most thick cloud is usually referred as eye wall. And outside, you can see those cirrus clouds. Now, if we go even further, just look at the GEOS, the NOAA geosatellite image animation, we can see very clear of the eye and also kind of the outside. Let me see if I can plot that. Yeah. So you can see, if you look at here, you can see a little bit here from the top. So here is the surface. And this is height. Right, let's see if you can see it. You can see there's a kind of stadium shape of the eye wall. That's a typical, very strong eye wall or animations of hurricane. And therefore, we also know that inside the hurricane, there's a stadium shape of eye that if you plot them together, you will look like this. So if you kind of Google hurricane structure, that's what you usually will see. The center of eye is here, and the cloudy is kind of getting bigger and bigger. So also because of now we can use satellite or we can use drone to measure, we also know the destruction is known. We can know better of destructions. And it's no longer just say it's causing destruction and it blows how long it stays. We see the damage. And we also know that a hurricane can cause huge damage and the dollar losses. And this is, I forgot which stone I'm using, but this is the before and the after of the ocean front. And you can see all the houses are destroyed because of a hurricane. So I think, I hope that give enough got some kind of background of hurricane. And in today's in today's talk, I'm going to do the 3 sections. The first one is kind of basic of a hurricane, and then I want to talk about how far out can we know if a hurricane is coming. It's also just a general discussion about hurricane forecast, because sometimes I got the questions often. And then we will go to more research-oriented topic about hurricane risk assessment and the limitation, which is focusing on how we assessing hurricane risk under a changing climate and what are the limitations we are facing in the research. Okay, Hurricane 101. So the term of hurricane, so the term of a hurricane, or now we have more general form, we are using is usually called the tropical cyclone. It's the general term for a cyclone or low pressure system that originates over the tropical ocean. In the place Atlantic and Eastern North Pacific, so Atlantic, Eastern North Pacific, we often refer that hurricane. In the Western Pacific, it's called typhoon. And in the Indian Ocean and the Southern Ocean, it's called cyclones. So hurricane actually has a more strict definition. It's usually is a tropical cyclone, has 1 minute average, usually it's called sustained wind, exceeds 32 knots in the Atlantic and the Eastern Pacific. Typhoon and the cyclone has the different intensity categories in the definition. So we are not going to go through today. Now, here we see in this image, there are 2 hurricanes in the system. You can probably tell me which one is stronger, which one is weaker by just looking at the satellite image. And that's because the hurricane intensity, sometimes it can detect from the satellite. And that's actually how we define the strength of hurricane before it getting close to land. At least in the Atlantic and the Eastern Pacific, if a hurricane is getting approach to the land, then NOAA will send out aircraft reconnaissance to directly measure the strength of hurricane using dropsonde. But before that, we all rely on satellite retrieval algorithm. So here shows you how we define hurricane based on the wind speed. Usually we use the Saffir-Simpson scale, which we describe hurricane from category 1 all the way to category 5. And before they reach hurricane, we call it the tropical storm or tropical depression. So only when the storm reaches tropical storm, only when a tropical cyclone reaches tropical storm strength, they will give a name. Otherwise, they will all give numbers, not name. Now, if you look at the satellite image from the right, you understand why I say you can kind of estimate how strong the storm is by simply looking at the satellite image. If it is tropical storms, even though you can start to see a circular wind, like spiral circular cloud, but they are not very well organized. And you have a pop-up convection, those like individual pop-up things everywhere. And once you start to become category 1, the spiral structure can become better and better. And when you become a major hurricane, which usually refer to when the storm has reached the category 3 strength, that's when we see a clear eye. And then if you reach to category 5, you see a very compact cloud with the center clear eye there. And that's, I believe the figures I'm showing you before are probably category 5 storms. Now, when the storm made landfall, even though there were, I kind of think this is Maria. Yeah, this is Hurricane Maria. Even though they were originally category 5 hurricane, when they make landfall, the lane interaction will kind of weaken the storms. And then you can see they drop the intensity and the eye opens again. When the eye becomes bigger and open, that's usually also suggesting the strength reduced. I believe Maria did reorganize later, but then once they go to the mid-latitude, they start to have a more symmetric structure. That's when we call it went through the extratropical transition stage. So we always like to look at the system when we look at the individual image, like what I just described. But for people like try to understand hurricane and how they interact with background climate, we prefer to look at all of them together. And that's what we usually call hurricane activities that refer to kind of collective the statistical behavior of storms. And this is just one of example. Here shows a historical track of hurricane globally or for tropical cyclone, be more precise, from 2000 to 2012. The color indicates storm intensity, and this is from observations. One thing we noticed that is all the storm, as I said, is more or less originated from the tropical region. When there's a storm occurring in the northern hemisphere, you see southern hemisphere is quiet, and vice versa. There's also a general direction of where storms move. In the northern hemisphere, they move westward and they recurve to the east. In the southern hemisphere, they also move westward but recurve to the south. So from here, we can already see some pattern, some kind of climatology or statistic of hurricane. For example, why when there's a storm happen in the northern hemisphere, there's no storm happen in the southern hemisphere? And that is because one of the necessary conditions for a tropical cyclone to form is the sea surface temperature. And that is controlled by the sun, by the season. So in the northern hemisphere summer season, which is usually from June to October, that's when the ocean temperature in the northern hemisphere is warm enough for tropical cyclone to form. And during the northern hemisphere winter, or I would say southern hemisphere summer, you can see the shift of the ocean temperature towards the southern hemisphere, and therefore that's when the southern hemisphere storm is going to happen. So the season between northern and southern hemisphere is separate. The season between different basin in the northern hemisphere and the different basin in the southern hemisphere are more overlapping. For example, Pacific is kind of wide and they have generally have Western Pacific warm pool. So they can have storms as early as May, as late as December. Such storm may also possible to happen in the eastern or in the Eastern Pacific or in the Atlantic, but it's rare. Usually for NOAA, the official definition of hurricane season in Atlantic start from June and in November. Now in the Indian Ocean, because of monsoon season, Indian Ocean has two peak hurricane season, which is before monsoon, before May, and after monsoon. I think, yeah. So other than sea surface temperature is a necessary condition for tropical cyclone to form. The formation and the intensification of tropical cyclone depends on other background information, like large scale climate information. When I say large scale, you can just consider is the background environment. And that is when we discuss in a more like a climate scale sense. So one of the requirement is the stone has to form at the area where there has a proper thermodynamic environment, meaning it has to be warm enough, has to be moist enough, etc. And usually this term is measured by a term called potential intensity. The potential intensity mathematically or theoretically, it means the highest intensity a stone can form can reach at a given thermodynamic environment. So we don't consider land interaction, we don't consider any other unfavorable dynamic process, which I will mention later. We only consider thermodynamic properties at any given location. And therefore, you can kind of have a potential intensity map. And from here, you can probably know, okay, this is a 2024 September map. So if any storm that form or passing through the dark blue area, they have a chance. If there's no other destroying factors, they have a chance to become category 5. And if they go into the purple area, they have chance to become category 4, and etc. Now, what are the factors that may destroy hurricanes? One of them, we call it wind shear. Wind shear. So wind shear is basically the wind at the different layers. Usually we consider low and high. Why does wind shear matters? Or why does wind shear matters? So remember we talked about hurricane structure is kind of symmetric and the spiral. And that's usually when the hurricane can intensify the most. But when there's a wind shear, because the wind at a different level have different strength, and they will kind of destroy those like nicely symmetric structure, and that disrupt the hurricane intensification process. And worse is if the environment, so let's say if they're already tilting the storm, but if the environment is dry, then dry air will get into the hurricane eye, and that we call it dry air intrusion, and that will also disrupt the convective system inside the hurricane eye wall and interrupt the intensification process. And therefore, the last important factor we are looking at is so-called relative humidity. It basically tells you how far atmosphere being away from being saturated. And that usually we look at the total precipitable water. So remember the previous slide on the potential intensity. Everywhere here is possible to become category 5 hurricane. But if you look at the image, you know here will not be good because there's dry air. And this is probably already another system. You can even see it. So now the last point I want to mention in the Hurricane 101 is about the tropical cyclone motion. So the tropical cyclone motion is controlled by the environmental background wind. But this time we were thinking of tropical cyclone as kind of a water battle, and how it pushed by the background wind. And one of the example is here. I believe it's also the same time. So there's a hurricane here, but whether it goes towards here or towards the other direction is based on the background where there's a high pressure here, there's a low pressure. So there's a high pressure here. Yeah, there's a low pressure on the other side. So these two together will shift the storm towards this direction. Okay. Now, if you have any question, by the way, feel free to stop me anytime as you want. We can discuss any unclear point more. So now we know the basic about hurricanes. We want to know how good the hurricane forecasts are. And these questions, this is actually not an easy question, because the first, if you ask me about how far out can we know if a hurricane coming or how good the hurricane forecast is, I will ask, what's your time scale? Hurricane forecast can usually be describing at 3 time scale. One is so-called seasonal outlook, which means we tell you how many storms do you have prior to the season start. And the seasonal outlook exists because we know hurricane activities highly depends on so-called ENSO status, or you can say El Nino and La Nina cases. For Atlantic, when during the El Nino condition, because the warm pool move more towards the east, and therefore it kind of increasing the wind circulation on the east. As a result, it actually increased the wind shear over the Atlantic area, and therefore it suppressed the hurricane activities at Atlantic during the El Nino year. On the other hand, during La Nina year, there's no suppression, and if you actually have reduced the vertical wind shear and other favorable condition, as a result, we have increased hurricane activity in the North Atlantic. So while I cannot tell you, and I don't believe anyone can tell you whether at our home in the New York City area, if there is storm coming or not, before the season, we can tell you how many storms may occur in the Atlantic basin, and that is so-called seasonal outlook forecast, which NOAA CPC will usually issue by the end of May or beginning of June. So how good is NOAA CPC's forecast is? So here is a mean square scale score. Basically, everything above 0 means your prediction is better than you just look at the past climatology. And this is NOAA's result. So NOAA is skillful and 40% better than you just get a number from the past data. And so you can kind of believe the number here. Of course, the question you can always ask, why do we need to know how many storms in the Atlantic basin? Maybe not necessarily important for you and I, for individuals, but I know there's a secondary insurance you can purchase in the beginning of June or the end of May, based on the hurricane season, which is probably for supply chain people will consider to do it. Now, other than give you numbers prior to the season, the second type of forecast we call subseasonal, which has been experimental forecasting product for years. And right now, the NOAA CPC issue them. I don't know how many people are looking at it, but this occurs as actually because the improvement of our knowledge in the tropical dynamics, specifically because of the system called Julian oscillation, which is convective system that propagate eastward, eastward at the so-called intra-seasonal time scale. And because if there are weights, then you can if in the area when the wave propagation related to Mendelian oscillation coming to the season and it's like a weight, so more convective induced environment, you can expect there will be more storms. On the other hand, if while during their propagation and they are the more dry blob happen to the Atlantic basin, then you will assuming the basin is less active. So what kind of information the subseasonal prediction gives to you? Better than the seasonal outlook. Subseasonal prediction tell you the probability of a given area, whether there's a storm coming. It still not be able to tell you when and exactly where, but it can tell you if you are interested in going to Madagascar, they will tell you over a certain area, what's the probability of the storm enter to this region. However, while the forecasting or the tool exists, most models are not skillful in predicting the probability. But we have realized that the non-skillful result is because some kind of systematic bias. So if we apply post-processing data, then the model can be skillful. Here, just one of example. The raw data is in the black, and most model lost their skill after 2 weeks. But if you calibrate it, you can see at least 2 out of 3 model here become more skillful. So again, this is semi-research product, semi-operational product, experimental focused product, but there's a chance in the future you may get more skillful information about hurricane coming to the area you are interested in 2 to 6 weeks in advance. Now, for everyone here, I believe if I talk to you about hurricane forecast, you are thinking of an image like this one. Those weather style forecasts that's 5 days, issue 5 days in advance, up to several hours in advance by National Hurricane Center. It can tell you when, where, and how strong a storm comes. It can tell you the possible rainfall rate along with the storm track, forecasting storm track. It can even tell you recently about flood risk and also storm surge height. So how good the forecast is. When we think about the hurricane forecast within 120 hours, we're mostly looking at landfall, intensity, and the location. So let's just look at the so-called track forecast. So it's where the storm is. And this is track forecast error. Don't ask me why they are in nautical mile, but they are in nautical mile from 1970 to 2000. And just give you a sense of what the number mean. So first of all, we see they all reduced from 1970 to 2020, which is good. And at least in 2023, if NOAA, if a National Hurricane Center issue you a landfall location 5 days in advance, then the average error, if they issue at New York, the average error is roughly 3.5 hours driving from New York City area. But if they issue it 4 days in advance, then the possible error area is 2 hours driving any direction from New York area. But if it tell you tomorrow there's a storm coming, you do better to pay attention because the average error is only within 1 hour driving away from the New York City. And that's assuming there's no traffic and you are driving more or less under the at the speed limit. So but the point of these figures is that since 1970, National Hurricane Track error has decreased by 2/3. And such improvement is actually because, again, the improvement of the science. The very first forecast is issued by Cuban priest, Father Benito Beniz, in 1875, who apparently, after studying so many past data, he can estimate if the storm is coming to Cuba by looking at the swell of the sea and the cloud motion. And then officially, United States start to really care about hurricanes because of the Spanish War. And after that, but that's just when we have reconnaissance flight can tell you the exact location of hurricane. But from there, we start to be able to build different models that to predict the hurricane track, start from more only know, just compare the current location to the past location, or just more statistical one. Or later on, we so-called statistical dynamics. So it's combine the statistical approach to some kind of dynamic model. To the later in 2020, 2000s, we have a better model from the GFDLO, and to now, there's a numerical weather prediction system where the National Hurricane Center's forecasters look at those data and come up with the forecast. Similarly, the intensity forecast is also kind of decreasing with time or improve with the error is improved with time. And that also is not as amazing as the track forecasting because intensification is a much complicated process. And how it can improve is also because the improvement of the science and the technology, especially computer, that allow us to have regional, very high resolution hurricane that we can actually simulate intensity very well. And the latest one is HFs. And you can see they can simulate like a cloud or rain band in a very detailed scale. So even though the hurricane forecasts are improved or there's new information generated because of improved science, people, if you today you ask any hurricane forecasters, ask them what's the most challenging things about predicting the hurricane. They will not say it's track or its intensity or landfall location. Some cases are challenger than the other, but they usually their forecast is quite on top, especially 24 hours ago. What is hard is to estimate the landfall impacts. So the hazards caused by a hurricane. And it's hard because once it get to the land, the impacts related to the size of the storm, the speed of the storm, the precipitation of the storm, and those are when the storm start to interact with land. And as I mentioned to you before, that is another process you have to consider and is less well understood. And sometimes the worst situation is even though the forecast is on top about the precipitation, but the communication to the local community is not efficient, and therefore they don't have good preparation. If people here are still are in New York City or metropolitan, New York City metropolitan area during the Hurricane Ida, which is 2021, you may remember how the city is flooded, and even place like Tarrytown or Nyack, the basement is flooded. The forecast of Ida is good. It tells you how much rain is going to drop. It just people don't usually consider the amount of rain and the duration of that rain going to drop because like 3 inches rain drop over a course of a day in New York City is totally fine. But over a course of 6 hours, that will causing huge flooding, and that's what happened during the Ida. Similarly, if you remember last year, Hurricane Helene happened that aftermath landfall causing huge flood and landslide in the North Carolina. It's the same situation. The precipitation forecasting is not bad, but once the rain drops to the ground, how does that causing landslide, inland flooding, and the people there has never experienced has never experienced hurricane, they may not have the best preparation. So that can lead to the third topic I want to talk about today is hurricane risk assessment and the limitation. So all the hazards end up we like to quantify it as dollar losses or mortality loss or number of people died. And if we look at the statistics, what do we see that tropical cyclone or hurricane, they cause the destruction and the money losses associated with them is increasing with time. So here I show the most costly hurricane in the United States. And you can see Allen and Katrina is in 2005, which is 20 years ago. The majority of them are all happened within these 10 years. And the same thing happened in other tropical cyclone basins. This is the most costly typhoon in the Philippines. And you can also see majority of them happen in the recent years. One can always argue that it's because of the development of the coastal cities, and which is definitely play a role. But at the same time, we also know the storm seems to be getting stronger and become more destructive. And every time things like this happen, you can start to see all those news on the articles. So the question, so now, if we want to know how to mitigate the risk, or even for adaptations, the first step to learn it, to do so is to evaluate of that risk. And commonly, there are several methods we can do. So we can just look at historical data, just look at what happened in the past. Or people like me will look at a global climate model, look at what happened to the past, what happened to the future. For insurance or policymaker or government, they use information from CAT model or catastrophic model, which usually is proprietary. They have very good things because unlike historical record and the climate model, we only look at hazard. CAT model, good things, they bring the hazard all the way to the losses because it's one big system. But they all have issues. Historical record is never going to be sufficient it's never going to be sufficient to give us full spectrum of risk because we just simply don't have that many high quality data. So there's sample error. Climate model, even for me, is going to be computationally expensive to run. And so it's not usually run by any other people, by people outside from academia. There's also no model biases, which we will talk later. CAT model, which because it's usually proprietary, so it's a black box. You don't know what's inside. They will not tell you. And every time you want new information, you write another check. And there's also traditionally CAT model is built more statistic based. So they cannot handle climate change because if the climate is changing, if the climate is non-stationary, then the past data is no longer able to represent the future. At Columbia, our group has been leading the effort to build a model for assessing tropical cyclone risk in a changing climate. We give a name called CHESS, stand for the Columbia Hazard Model. What is a Columbia Hazard Model? So it is so-called statistical, dynamical, downscaling model, meaning that you get information from so-called global climate model. You look at the larger scale information, which I introduced earlier, potential intensity, shear, humidity, and other variables, how they change with different climate or how they are in the historical climate. And you put it in this arrow called CHESS. Then you generate a bunch of synthetic storms that can give you sufficient number of cases to the area you are interested in. Because it's using global model, so if I'm interested in how the climate change works, how the climate change affects the final stone hazel here, I can just give you different, force the model with different future scenarios. So it can able to address climate change. The chance model itself is not those we used to do the weather prediction, very complicated, high resolution. Instead, it's a simple three equation describing genesis, track, and the intensity. They only use a handful of variables to describing the shear, steering flow, thermodynamic property, and the vorticity is another dynamic property I did not talk about. And the wind, daily wind, it just for the track. So because of this, they are usually cheap to run and it's computational, so there's no sample error once we generate a bunch of events. Now, it is also global and climate sensitive. So different climate information, you get different data. The model was designed to be open source and was released in 2020. And so that gives us an advantage over the proprietary K model is not a black box. Although the model does have some uncertainty that is carried over from the lack of understanding in the hurricane genesis. So here is just saying, if you are asked like, what's the future number of future hurricane annual number will be just how many storms will happen in a basin, for example. The answer is we don't know because the model tell you it can be go up or go down, depends on how you describing the change of atmospheric moisture. And that is actually a scientific uncertainty because we do not have a hurricane genesis theory. We have basic understanding what are the necessary conditions for hurricane to form and what are the favorable and the unfavorable conditions for hurricane to form. But we never really can describe theoretically about the cyclone genesis. So apart from there, the model has a different hazard component that has wind that can take care of storm surge and that can take care of precipitation. In short, I can probably say problem solved, but not so fast. There are several challenges, and today I think in the next 10 minutes, I just want to talk about one of a new challenge that recently been noticed, but is important one, is the error of the future projections of the global climate model. Specifically, all the global climate model all project future to be a so-called El Nino-like warming future. But as I will show you very soon, that projection is inconsistent to what we have observed in the past, despite the global has been warm since the Industrial Revolution. And we are arguing that all the models are wrong is because there's model bias that exists in every single global climate models. But before that, let's talk about why we care about the future look like El Nino warming pattern. Well, I can touch on that in the seasonal prediction. So El Nino is an event that happen in the tropical Pacific. And this is just how, let me see if I can, yeah. Yeah, this is just how El Nino developing, and you can see a warm anomaly in the Eastern Pacific. And as I said, even though El Nino or La Nina or ENSO is an event happening in tropical Pacific, it has an impact on hurricane activity in Atlantic. So this is from NOAA image. It shows few hurricanes during El Nino, more hurricane during La Nina, I mentioned before. And if you look at El Nino minus La Nina year, you also see the track density anomaly, which is just another way to show it and show the ENSO impact is not only in the Eastern Pacific and the Atlantic, but also occurring in the Western Pacific and in some other southern hemisphere tropical oceans. So despite the global climate model has been projecting a more El Nino-like pattern, which I just showed you before, and this is model projections, you can see it's more warming in the Eastern Pacific. Historical observation has shown the opposite. That is showing more cooling in the Eastern Pacific. And if you look at the track density plots from tropical cyclone, so by the way, the top is sea surface temperature. The bottom is so-called track density. It's coming from the stone tracks. So stone activities I showed you before, but we just make a density plot of it. If you look at the track density plots, you can, and if you remember what I showed you earlier, the previous slide, you can also see that the track density from global model has a more El Nino-like pattern with reduction of storm activity in the Atlantic, especially Gulf of Mexico region. While in reality, during the past 40 years, there's actually increased hurricane activities in Atlantic basin, and which is correspond to the La Nina-like SST in the Pacific region. So how does that link to the risk? Does that matters? Is this just, if there's no impact on risk, then we don't need to care, right? So a recent work that by our previous postdoc, currently a professor in Cornell University, he looked at how tropical cyclone hazards in the Hong Kong area. So when we talk about tropical cyclone hazards, one common way to describing it is using so-called return level plots. Here shows x-axis is the return level, so intensity within like 100 kilometers within Hong Kong region. And the y-axis is return period. So if it's 100-year events, 200-year events, or 50 years events. And what the figure here shows is that we only need to look at the blue and the red line, showing that the risk of typhoon impact in Hong Kong at the pre-industrial control period, so no climate change period in the blue, and warming climate from 2050 to 2100 are almost the same. The changes are so small. Is that really true? So then he further look into it, he realized the typhoon risk in Hong Kong has dependent on the ENSO status. When it's the strong La Nina, you have let's say, yeah, you have let me see, 100 become twice. Yeah, during the La Nina year, you have much stronger, much weaker risk compared to. So, let me say that again. So during the La Nina years, you have much stronger risk compared to during the El Nino years. Yes, that's true. Yeah. But then if you look at the historical and the future period results, if you only look at La Nina year, you can see the risk is increasing. So, and you do the same at the different neutral or ENSO El Nino year. If you just bin the data based on ENSO status, the risk is always increasing. But the results are showing the same is because the whole system moving towards El Nino warming pattern. Therefore, it muted the increasing risk in the climate projection. So I hope this is just an example to show you that the errors in the warming pattern will actually result the errors in the assessment of risk. So now the question you probably ask, why does the model and the observation look different? Is that simply because of observational error, we cannot actually measure her like a SST in the open ocean easily. We always rely on the satellite data. Or it just in the past 40 years, there's some kind of strong Pacific decadal oscillation, so it's not actually climate signal. Or observational trends are real and the model is wrong. So there's several studies to show that, first of all, it's unlikely to be observational error. And the reason that support the La Nina-like pattern, including aerosol, Southern Ocean, but one of the most interesting one that developed by Lamont scientists is so-called ocean thermostat effect. What it means is that when the global ocean is warming up, but usually you warm up at the surface. But in the equatorial Pacific, where especially in the Kotan region, where that control the ENSO variability, the water is actually from subtropical subduction, the subduction water from the subtropical region that upwelled at the equator. And those subsurface ocean does not warm as fast as the global mean temperature or as the sea surface temperature because of the high heat capacity of the ocean. And as a result, that's why even everywhere seems to warm up, but the area where you have strong upwelling in the equatorial Pacific, that will remain to have cold water that is not yet impacted by the global warming. And therefore, as a result, you have a so-called La Nina-like pattern with colder SST even colder in the equatorial Pacific. And that usually we will see it increasing the gradient of both zonal and meridional gradient compared to the El Nino-like pattern. And this is just an image we look at the observed data, all suggesting the increasing trend of zonal and meridional gradient compared to all the model spread. So model does have some going to the La Nina-like pattern, but none of them is as strong as the observations. And so Seeger et al., Richard Seeger is a scientist at Lamont, they argue that the model cannot capture the ocean thermostat effect and thus failed to generate the observed La Nina-like pattern. It's because the bias in the Pacific Kotan region, and that persists over the generation of global model bias. That is, let's say, we start to run the global model together in 1960, and that bias has been there forever. So in this specific research, our group design a project, just say, have basic idea is model is wrong, like causing the wrong projection of SST pattern in the tropical Pacific, and they cause the error in the projected tropical cyclone activity. We ask, what's the alternative projection if we correct the model bias? And can we use the ENSO analogy to describing how tropical cyclone will respond to the global warming, since the world is heavily controlled by the tropical Pacific SST pattern. I'm going to skip a little bit, just going to jump into results. Basically, a postdoc working with me shows that when we remove the model bias, the model will project a La Nina-like projection, just like observation. And again, I'm going to skip the detail, but here is the bias in the model in the beginning, and you see the blue is called bias in the tropical Pacific. We can remove it using some fancy mathematical method from here to here. And this is result. So the FA is the one has bias removed. If we compare it to the one without the bias removed, we can see a more La Nina-like pattern. And we can also go back to the original scatter plots. You can see control and with bias removed getting more close to observations. Although we also show that this La Nina-like trend, which is here, in the blue one from the bias correct version is actually going to transition back to El Nino like warming in 2050. So basically, we just say the La Nina like pattern we are looking at here right now may be transient. And you will still transient back to El Nino like warming, but the timing is uncertain. This model suggests 2050, but we don't know what other model says. Now, the next questions we try to answer is, can we apply ENSO analogy to the future tropical cyclone projection? Long story short, I'm going to use chess downscale by those models. I show you the scatter plots. Each dot is each models. All the model from two group and just look at the differences. See if the difference is similar to the ENSO anomalies from those model. And the answer is no. The ENSO analogy is not the best framework for communicating future trend in tropical cyclone. And that's just because this is the La Nina-like observation from the satellite data. This is so-called basic La Nina-like anomaly, and you can see they are quite different. I think that lead to the conclusion of today's talk. I give some background of tropical cyclones, mostly for fun, but I also introduce our work on the chess model. And we say climate change is expected to increase TC hazards, but the changing is highly sensitive to the warming pattern, and which may be wrong right now. And that's because of the mean bias in the global warming climate model, all of them. And on top of that, even though we commonly use El Nino-like or La Nina-like SST pattern to describe in the warming future, but they are not, ENSO is not the best analogy to discuss future tropical cyclone hazards. I'm happy to take questions. Thanks, everyone.
Thank you very much, Jake.
Mm.
Uh, we'll open the questions up to everybody who would like it. Otherwise, I'll start with my question.
Thank you.
One of
Sure.
the re one of the interesting things is there's no hurricanes in the South Pacific, South Atlantic.
Yeah, so South Atlantic is usually colder and has stronger shear, so has stronger shear in that area. Therefore, climatologically, they don't usually have hurricane forms there. There are, if you look at the more like a revised data sets, there are a couple of them, but it's really rare. Eastern South Pacific is too cold, just in case people are wondering too. Because there's a strong upwelling and also connection with the Southern Ocean there.
Okay, good. Some other questions from people? We're looking at the acknowledgments right now. That's a very powerful group of people there.
Yeah, the work is done with other than the postdoc photos I show, the work is heavily involved with four senior colleagues I have, Eden Sobel, Susanna Camargo, Michael Tippett, three of them plus me, together we designed the chess model. Richard is the who give us the big assumption on the tropical Pacific knowledge. Yeah. So
It looked like Mark Kane was with you in some of the papers you were doing.
yes, so I mean, Richard's argument is originally from Mark Kane's work. Yeah, so it is related. Yeah. I think even when I read the proposal, I also talked to Mark Kane about it too.
Right, about 30 years ago, Mark was part of the team that first predicted El Ninos,
Yes.
which was a
Yeah.
major advance.
Yeah.
And Susanna comes from part of the world that I like very much.
Yeah, Susanna is like doing lots of climate and tropical cyclone research. Yeah, so the Genesis index, like Genesis component of the chess model is actually from Susanna and Mac Tippett. Yeah.
The other thing I'm amazed about looking at this picture is how you managed to get all these people to stand still for so long.
Well, it's ocean department and we have tea time every Friday, so we just say you have to stand outside until first before you can get the tea and cookies.
Okay, sounds good to me.
Yeah.
Okay, any other questions here?
It was a great talk. Thank
Thank
you.
you. Thank you.
Very nice. Okay, so we're going to record this and post it on the Earth2Class website,
Sure.
and then people will be able to see it at other times as well.